Okay, well, thank you ever so much, everyone, for coming along. Lovely to have you here today. We're going to be talking about slice to volume reconstruction of fetal MRI. And we're going to start with an introduction to fetal imaging and then look first of all at the classical method and two particular techniques, which are slice to volume registration and super resolution reconstruction. We'll then be in the second part looking at deep learning methods and then drawing our conclusion from this. So why do we image the fetus? So first of all, ultrasound has been well established as the first-line modality for fetal imaging for assessing development and also identifying any potential abnormalities. But second-line imaging is needed to clarify any uncertain findings and investigate any abnormalities further. For example, if looking at the brain's development or identifying congenital heart diseases. And of course, for research, of course. So our fetal imaging modalities, as I said, ultrasound, which is used for routine screening, but also for fetal echocardiography. There's also MRI, which is becoming increasingly popular for second-line imaging, and CT, which we're not going to discuss in further detail, but can give extra bone detail, but is rare due to the radiation risk. So we're going to be focusing primarily on MRI, but there will be some mentions of ultrasound as well later in the presentation. So some of the challenges that we face when we're trying to do MRI scans of the fetus, first of all, and as you can see from this image, is very much motion. You can see that the fetus is wriggling away happily, but also if you look closely, you can see the maternal respiration, and both of these affect the motion of the image. And also image quality, particularly signal to noise ratio, and that can be especially affected by the BMI of the mother. So how do we sort of overcome those challenges? First of all, we generally wait until the third trimester for doing our scans, because as you can see, the fetus is far more restricted in their movement. We begin by acquiring stacks of 2D slices because we can acquire the slice much faster, and that reduces the risk of us capturing any motion within one slice compared to if we were trying to scan a volume. That takes longer and we're more likely to get motion corruption happening. So we generally do stacks of slices. It's faster, but also we repeat it. So we'll do multiple stacks over multiple orientations, which increases the probability of us actually capturing those structures accurately. So how do we compensate for this fetal motion challenge? So interslice, so the motion that happens between each slice capture, we compensate for this using a technique called slice to volume registration, which we're going to talk about. But also some motion may happen within the slice capture, so intraslice motion. And one of the things we do is data redundancy. Because we've done multiple stacks of the same area, hopefully we've caught enough of the detail about each of those sections to be able to reconstruct it. We try to identify and discard any anomalous data caused by motion using our robust statistics. And then we combine all the information within the stacks using super resolution reconstruction. And we're going to focus particularly on slice to volume registration and super resolution reconstruction in this next section. So I'm going to begin by introducing our classical method. And this was originally posed as a 2D to 3D problem back in 2012. So in order to reconstruct the fetal brain. So beginning with stacks of 2D slices, which contain rigid motion, and you can see how the slices aren't well aligned. But the motion is rigid because it's contained within the skull boundaries. And using the algorithm and the classic method, we're able to reconstruct a nice 3D representation without that motion. So we start with slice to volume registration, and the goal of this is to compensate for the motion that happens between slice acquisition by aligning individual slices within the reconstructed volume. And this produces a rigid transformation for each slice, which is basically translation rotation. So you can see the stack is going to be acquired in order, but actually once we work out where it goes in the final volume, they'll be slightly adjusted in terms of their position. But the way we get to this point is there's a few steps. We begin by acquiring our stacks in multiple different orientations. We then register the whole stack to a chosen template stack to estimate the initial alignment of all of those slices and see how those stacks fit together. Third, we perform a reconstruction using those initial alignments. And finally, once we have a reconstructed version, we can register each individual slice to that reconstructed volume. And using that, we can then redo the reconstruction using the new alignments and repeat that to improve the alignment estimates. But if we just drill down a little bit more into the super resolution reconstruction process. So our goal here is to combine our lower resolution slices with one higher resolution volume. And you can see the difference in resolution between these images. And we can only do that because we've got multiple different slices of the same area. So how do we reconstruct the 3D slices? We begin using that initial estimate of the alignments, or whatever our most recent estimate is, and we perform a Gaussian reconstruction, which gives us a rough, blurred version of the volume. We then use that to initialize our volume to start with, and from our volume we can simulate what we think that slice should look like, and that's our forward model. And we do this using a point spread function. So what this is basically doing is it says we've got an elongated 3D Gaussian, and it's elongated because of the thickness of the slice. And that is basically saying that there's a set of points within our volume will correspond to one particular voxel in our simulated slice. We then compare the simulated slice with the acquired slice, and from that we can calculate our error between the two. So once we have that error, we can now solve our inverse problem by trying to minimize the error between the simulated slice and the acquired slice. And we do that with sum of squared errors. Oh, not sure why it's moved on. And then once we've done that, we can iteratively update the volume using gradient descent in order to improve our estimate. So in addition to those two methods, we also do robust statistics, and this is where we try to exclude any corrupted or misaligned voxels and slices based on the error between the acquired and simulated data. And we also do some intensity matching. So the bias field in the scanner won't move with the anatomy. And as well as this, there are MR artifacts such as spin history and interaction between MR signal and motion. And all of these things mean that we need to make some adjustments to the slices in order to match what we're expecting them to look like in our simulated slice. So we add these calculations in as well. So I'm just going to put all of those concepts together and see the full classical method in one slide. So we start with our acquired slices, acquired stacks, and we begin with our slice to volume registration process. So we have our volumetric registration. We get an initial estimate of how all the stacks fit together. We then create our Gaussian reconstruction, and then we pass that into our super resolution process. So we have our updated volume. From this, we simulate our slices. We calculate the robust statistics and intensity matching, and then calculating the error. And then this gets repeated a set number of times to iteratively improve the volume. Once we're happy with the volume, we will then exit, and we can do our slice to volume registration to accurately try and align those slices within the volume before we start this again with the new alignments and do a Gaussian reconstruction and so on and so forth. So overall, we do the slice to volume process, iterate over it 3 times. We start with the volumetric registration, and then we improve with the slice to volume registrations. But internally, we do super resolution reconstruction. On the first couple of passes, we do it 7 times, and this is just really with experience of what works well. And the reason we do it fewer times, the first couple of times, is because we actually only really want a blurred output from that, because we don't want the registration of the slices to get stuck in local minima. However, on the final time we do it, we will increase that to 3 times the amount, 21 times, so that will give a crisper and more precise reconstruction, which we want to finally output to the user. So once we've done all that, we can output our final volume, and that's the summary of the classical process. So since that method was proposed, there's been various different extensions of the classical method. To start with, there's 3D plus time and also plus velocity for cardiac. There's been work done on deformable reconstruction using deformable registration, and this is good for any parts of the anatomy which aren't contained in rigid boundaries, such as the abdomen, placenta, and there's an example here with the lungs. And there's also work being done on diffusion and quantitative mapping as well. But I want to focus on one particular application, which is the area that I'm working in, which is 3D plus time for fetal cardiac. So congenital heart disease affects 1 to 2% of all pregnancies, and we want to use imaging techniques for segmentation, such as working out the ventricular volumes, to be able to measure cardiac function, such as ejection fraction and stroke volume, and also shape analysis to predict diagnosis. And this is an example of a coarctation of the aorta. So we use the classical method and we add time as an extra dimension onto that in order to be able to capture the movement of the beating heart. But we have an additional challenge, which is the lack of an ECG signal, which would normally be present when doing a cardiac MRI. So thankfully, there's been a recent development of a Doppler ultrasound device called SmartSync, which can actually go into the MRI scanner on the mother's abdomen and be able to provide that missing gating signal for us to know where a fetal heart is beating. But this device is most reliable during the 3rd trimester at present, because the fetal motion otherwise can take it out of range. So this is our new 3D plus time problem. And you can see on the left, we've got our stacks of 2D plus time slices, which have been acquired from the scanner. Now, each of these slices takes about 4 seconds to acquire, which does slightly increase the risk of there being motion within the slice. But also, what's really nice is the data then gets interpolated on the scanner across a single cardiac cycle because of the benefit of having the gating. So we're able to use this with the time dimension, the classical method, to produce a 3D plus time reconstruction of the fetal heart beating. So I want to just pause and think for a moment about a concept of gated temporal acquisition, because the way this works is quite important to some of the assumptions that we make in this process. So if we imagine we have a timeline with the fetal heart beating, and we want to capture just one single heartbeat, and we're going to do that for simplicity with 3 frames. So let's assume we're in our first time window and we want to start capturing the image data of our first frame. So we start to put some data in there. Then as the timeline moves on, we enter our second window and we start to collect data for our second frame, and our third window we start to collect data for the third frame. But then time goes back to that at the first time frame, so we continue collecting for the first one, and the second one, and the third one. And we continue this process until we've filled up all 3 frames of the image data that we require. Now imagine for a moment that the fetus moves in the middle of this process, so somewhere around here. Any movement is going to be represented in some part across all of the frames. It's not just contained, as you might intuitively think, in the later frames in the cardiac cycle. So that motion is present across all frames. And from that, we draw an assumption that the frames are effectively locked together in time with respect to motion. And that enables us to have some really nice efficiencies as we go on. So let's look first at slice to volume registration with the time dimension added. So we've already introduced concepts of volumetric registration and per slice registration. So now we're going to extend it. So we know that the parallel acquisition of all time frames happens within a slice, and we assume that motion is the same across all frames within a slice. So because of this, we're able to just register one time point of our slice within the volume, and then apply that to the whole stack or slice. So now we have super resolution reconstruction with time, and we want to apply the time dimension. So we start with the reconstructed volume, and you can see the time and the heart beating. We then simulate the acquisition as we did before, and we use the spatial point spread function, same as with the 2D to 3D method. But we also now have a temporal point spread function. But because the timeline is interpolated on the scanner, we don't need to reinterpolate it at this point. So we can just treat this as a one-to-one relationship, which is really nice and efficient with gating. Now we can compare that to the acquired slice, calculate the error between the two, and update the volume using that information. So hopefully you can see the similarity here with what we looked at in the original method. So we've taken this and we put it inside a fully automated pipeline, which will take our stacks of 3D plus time slices. We segment the fetal thorax and do our reconstruction of 3D plus time. But this will be oriented to the orientation of the mother, so we now need to do a reorientation in order to get it the right way, at the right orientation for the fetus to produce our final output. So our result is that we have an automatically reoriented 3D plus time fetal cardiac reconstruction. And when we've compared this to the previous technique that was done without gated input, we were able to get equal, slightly improved in quality, but about 10 times faster with gating, which has been a huge improvement. So next steps of this technique is improving the quality of acquisition, because that will have a direct impact on the quality of the output. We want to also add blood flow velocity from the gated phase images, so we have 3D plus time plus velocity, and then start adding shape and flow analysis to identify biomarkers of congenital heart disease in utero. So just to summarise this section, so the classical method was first published in 2012 for 2D to 3D reconstruction of fetal brain images, and it interleaves the concepts of slice to volume registration and super resolution reconstruction to compensate for motion. But new applications are still being developed and worked on using this method, such as 3D plus time for fetal cardiac, because it is really an effective solution for both intra and inter-slice fetal motion. But it is a complex and memory and time-consuming algorithm, so there's now work being done in terms of deep learning to see how we potentially might improve on some of these things further. So with that, I'm going to hand over to my colleagues.
Okay. So yeah, I'm gonna focus on how deep learning has been applied for SVR. So actually, there have been works that have looked into using deep learning within the SVR pipeline, keeping like the SVR itself using the classic algorithm, but actually automating certain steps with deep learning. So this is exactly what Naomi was just presenting in fetal cardiac. For example, you have automated thorax masking, and then you have, as a post-processing step, reorientation. But me and Helena are going to focus more on actually deep learning to do the registration step. So when we want to register slices to a volume, and also in terms of super resolution reconstruction. And we'll go through some important references. So in terms of what exists in literature, most of these methods are actually trained in a supervised way. So it's a rigid registration problem, and one of the first references is SVRNet, which in this case is actually not fully deep learning. So their method was step number 6, which so effectively they have a network with the goal of improving the initial alignment of your slices to the reference space, and then actually using these corrected slices as input to the classical SVR algorithm. So the use case more for this was for data that is very motion corrupted, where classical SVR fails. But yeah, I thought I'd explain this method because it's actually a baseline from where a lot of the references that me and Helena will be talking about build on. So yeah, as I was saying, it's a supervised technique. So you start from having some pre-aligned good quality training volumes that are all rigidly aligned to the same 3D reference space. So the idea is you can then simulate slices during training, and you know your ground truth transformation. So in this case, it was a simple CNN, and I'll talk a bit about especially how the transformation is parameterized, but also how to simulate the slices. So the goal in this case is to evenly sample all possible 3D transformations without bias in any specific type of transformation. So you can formulate the problem as you effectively want to evenly sample your plane surface normals across a 3D sphere. So if you were to just randomly sample between your azimuth and your elevation angles between their ranges, what you would get is actually accumulation at the poles because of the curvature of the sphere. So an equal increment in your elevation angle does not equate to an equal amount of surface area being covered. As you can see at the poles, it's much less. So therefore, you would be biasing the transformations that you're sampling during training. So actually, this can be simply corrected by adding an arc cosine term which accounts for this curvature. And also what they do in SVRNet in this paper is a deterministic approach, which is Fibonacci sphere sampling. So in this case, it's not just trying to randomly sample points with equal probability, but you're actually trying to distribute a set of n points so that they're evenly spaced across a 3D sphere. So you start from a set of n number of points, and you also take into account the index of the point that you're looking at. And effectively, this method first starts by evenly distributing your points across the altitude direction, and then rotating by the golden angle, and you get something that looks a bit like the sunflower seeds in a sunflower head. And this is what they use in SVRNet. So this is just for 3D rotations. If you want to also simulate in-plane rotations, you need to rotate again about your z-axis, and you may also want to add in some tx and ty translations. So in terms of how best to parameterize your transformation, what your network is actually predicting. So as a reminder, this is rigid registration. Quite an intuitive approach is to represent it using Euler angles and then 3 translation parameters. So obviously we need to first account for the circularity of rotation. So this is just a 2D example, but effectively accounting for, if you're just using, for example, absolute error or mean squared error, the fact that you go back from 359 to 0 should be an error of just 1 degree. So this can be accounted for by using a wrapped error. And this has been used in literature, also extending the same formula to 3 Euler angles. So this is an option, but it's maybe not the best option if you want to sample all of your 3D transformations, because Euler angles have some challenges to work with. One of these being that you can represent the same final 3D transformation by a different combination of Euler angles in certain cases. So if you can imagine your network predicting a set of Euler angles and then your ground truth Euler angles look different, but actually it's the same final transformation, this could lead to instability in training. So in some cases, it can be tackled by just restricting your range of Euler angles that are being sampled, but actually potentially parameterizing it with a different transformation might be more fitting. So axis angles and quaternions have also been explored, especially quaternions are apparently much nicer to work with, but they're maybe less intuitive to understand. But what they use in SVRNet is actually an anchor point parameterization. So in this case, you're representing your rotation as a set of 3 points in a plane. So the location of your plane in 3D is defined by 3 points corresponding to the center, bottom left and bottom right corners. So then this effectively is just L2 loss between your ground truth and predicted points. And one advantage of this parameterization is you're also taking into account translations. So in the previous one, you'd have to be balanced in 2 terms, whereas in this loss function, you're not. And effectively, in terms of going between this parameterization and rotation metrics, you're effectively just taking a set of vectors connecting these 2 points and then cross product between these vectors to form your new basis, if you're interested. So in terms of results of SVRNet, so here they were looking at cases that are severely motion corrupted. So the first 3 columns are actually the input. And then they were comparing it to, I guess, state of the art at the time also, which you can see is very blurry, so patch to volume registration. And then SVRNet, so this column E is effectively what it looks like just by taking the output of the network. And then column F is, I guess, the best version. So when you first improve your initial alignment of your stacks of slices using SVRNet, and then you feed this into the classical SVR algorithm that Naomi was just presenting. So this is one of the first methods that was proposed, but actually in this case, the network is just taking 1 slice at a time. And there is a lot more information actually that could be leveraged for each patient, because in reality you have lots of maybe stacks of slices or a full sequence. So actually using this context information for every patient could potentially really help improve accuracy in a deep learning model. So the references I'm going to talk about are more geared towards ultrasound, and then Helena will explain some quite similar ones for MRI. So just as a reminder, what Naomi was saying, that ultrasound is the primary modality for screening, for fetal screening of main organs, brain, body, and also cardiac. And even more for detailed examinations when there's suspicion of cardiac abnormalities. So this is still a 2D modality, really. What's used in clinic is still freehand 2D ultrasound. So 3D technologies exist, but they come at trade-offs. So you can see here, these techniques still suffer from a lot of motion corruption. There's also an anisotropy in the resolution, and they generally have lower temporal and maybe also spatial resolution compared to 2D. And it's quite challenging to acquire a good 3D volume where you can see all of the structures with no shadow artifacts, for instance. So actually, in practice, all assessments is still generally done using 2D. So in Plain Invol, this paper from a group in Oxford, they were trying to address, in this case it was fetal brain imaging using ultrasound, and provide some more 3D context to these screening examinations. So in this paper they do actually look at leveraging for every patient the full information that you can get from a whole sequence, for example. So the architecture has a CNN for extracting features for every frame of a given subject. And then they have 2 modules. So they have a comparison module where you concatenate pairwise feature vectors from all of your input frames and pass these through a fully connected layer. And then they have an attention module, which is looking at the relative attention between pairs of your feature vectors, effectively. And then their prediction module is just combining this information of your pairwise comparison feature vectors with your attention scores. And their final linear layer outputs a set of anchor points. So again, they're using the same parameterization as SVRNet. And it's, again, this one was trained also in a supervised way. In this case, they were using 3D ultrasound scans that are generally lower quality than 2D and less accessible also. So in this case, they show, so the baseline is SVRNet, and they show actually this is increasing number of input frames for the test cases. The errors, so this is Euclidean distance, you can see it decreases, up to a certain amount. So actually adding more context is quite helpful. And this is also for plane angle and similarity. And this, I think, was using simulated on unseen volumes, so simulated slices, but then they also tested on real 2D scans that were manually annotated by two different experts. And yeah, this is just one of the examples that they propose. So this paper is just, again, tackling the SVR part. It's just rigid registration without the full reconstruction, so without any super resolution or anything. So in subsequent works, actually, the same group proposed a more complete framework, which they call implicit vol. And in this case, they were aiming to combine what plain vol had learnt in terms of accurate localization with an implicit neural representation to actually learn a continuous representation of all of the of a given volume at a time. So I won't go into very many details, but just very briefly, effectively, what this looks like during training time is you have your set of ultrasound images, then plain vol generates the prediction of where these are located in 3D. The coordinates for every input are then rotating, and then these coordinates are used to train an MLP to output intensity values for every location. So you can then query any coordinate and find out the intensity value if it's been trained. And they also look into fine-tuning for every subject plain vol during training, so effectively updating both networks, the localization one and the MLP. One issue with this approach is that it doesn't actually account for the view dependency of inherent to ultrasound. So actually, this is quite an important problem, because in ultrasound, depending on where your probe is located, you would have different artifacts. So you might have different intensities, you might have shadowing. And so the previous approach didn't really study this at all. So I'm just going to briefly go through this reference, which was UltraNerve for ultrasound view rendering, which is quite an interesting alternative for accounting for this problem. So yeah, this is not doing registration. This is more just for view rendering, accounting for ultrasound physics. So in this case, rather than having a network that is learning directly intensities, they propose a model that learns specifically inherent tissue properties, so tissue properties maps, and then they use an ultrasound rendering model that combines these 5 tissue parameter maps to actually construct the B-mode image, and a B-mode image is just the standard grayscale ultrasound. So very briefly, again, your input is a set of coordinates, and then you have your MLP layers, and the output from the INR is, in this case, not directly the intensity, but 5 ultrasound-specific parameters that depend on your tissue type. And then they use these predicted maps and like an ultrasound-based rendering algorithm that was based on some previous work to then can output the specific intensity and then train this model. So it's actually the rendering algorithm uses intensities at each query location and also all of the preceding ones. So here, just an example of some of their results. On the left is the ground truth, and then the center ones are alternative approaches. So this is one using compounding, and this is just an INR without any of this specific rendering. And then the one on the right is actually UltraNerve. So this is a test view that wasn't seen in training. And what they're trying to demonstrate here is that you can observe this shadowing artifact, which is view dependent, by using this model. And this model was trained with known ground truth transformations where they had a tracker also. So they knew the very specific locations that their training data came from. Yeah, and if you're interested here also what the different tissue-specific maps look like. Yeah, so now I'll hand over to Helena to go back to MRI. Okay, from you.
Yeah, so now I'm going to talk about this deep learning-based framework. So it's called NAS4, and it actually tackles both size to volume registration. So this part is called SVORT, and as well the reconstruction part
which is done by using these neural implicit networks. So overall, it works. This whole architecture works as a first step. They train this transformer model to learn how to register our 2D slices in multiple stacks to a 3D template. And once this is optimized, we then learn how to reconstruct our 3D volume by using this implicit neural network. So NESFORG has mainly shown advantages in fetal and neonatal reconstruction, since it's where we usually have a lot of motion. So I just put here some 2 examples that they show in the paper, where you can see, hopefully you can see here, but it just shows that NESFOR can tackle some artifacts that the classical methods, which is SVRTK here, have. So, and as well for neonatal cases, they show that as well NESFOR in some subjects where there is severe motion, NESFOR is able to reconstruct them compared to classical methods. So I'll just start by describing the SVORT part first, so our slice to volume registration. So these figures here are just an overview of the architecture of SVORT, and as well this pipeline for the interactions that SVORT goes through. So in summary, the SVORT architecture just uses is based on using these transformer models to predict our residual rigid transformation updates for every slice, as well as an estimate of our current 3D volume. And as well, just an important note is that basically the authors propose to use transformers here, since they can inherently just enables us to tackle this dependency that exists between slices when we are estimating rigid transformations. So I'll now briefly describe how the SVORT pipeline runs, and then we'll look into it with a bit more detail. So SVORT runs for k iterations, and at each iteration, it firstly just predicts the residual transforms. So this is what we call the delta t for all of the slices that we have. And this is done by using a transformer, which they call SVTT. So this one you can see here. And then this updates our transformation for the previous iteration and re-estimates the volume with the newly updated transforms, and just basically repeats this process for our k iterations. So now let's look a bit more into detail how this whole training pipeline goes. So training SVORT is actually done in a supervised way as well. So this means that we have 2D slices that are artificially sampled as training data from this 3D MRI high quality volumes of fetal brains, which usually they just use subjects that have little fetal motion, just so they can guarantee that it's going to be more high quality. And so this way we can have our ground truth slices, which are these slices, so we can simulate each slice, so each slice y, using our simulate slices y hat from the current 3D volume x hat. And this is done by using the previous transformation from our previous iteration. So in the case where this is our first iteration, they just initialize it with the identity. And then we just pair our simulated and ground truth slices. We concatenate them and pass them through this ResNet to get these slice features, which will go into the transformer alongside our positional embeddings. So these positional embeddings are just our stack and slice indexes and our estimated transforms from the previous iteration. So once all of these go through this transformer, then the final linear layer just regresses our residual transformation, so our delta t. So after then this transformation is updated by using this delta t that we get from our transformer, we can now do a new estimate of the new volumes that we have. And so this is done by firstly computing here a point spread function based reconstruction, and then inputting that alongside with our updated transformation and then ground truth slices to this second transformer that you can see here. So they call it SVTX, and it has the same architecture basically as this previous transformer that we were looking at. And all of those are just finally imputed in a conjugated gradient solver, which outputs our new estimate volume that is then used for our next iteration. And then this process just repeats itself. So like I was saying, we just have here a little summary of all of these iterations for SVORT, just so that we can actually see that the total loss of SVORT is actually this LT loss, which is just basically an L2 loss between our predicted and ground truth coordinates at anchor points of slices. So this is just the transformation loss that Paula was talking about by using anchor points. And we have as well this loss, which is between our estimated volume and our ground truth volume. And so both of these losses account for the total SVORT loss. So now I'll look as well at how the actual process of reconstruction happens through implicit neural networks. And so we have here as well an overview of this pipeline and architecture, in which our goal here is then to reconstruct this 3D continuous volume that explains our observed slices. And so the NESVOR just models this 3D volume as a continuous function instead of just representing the volume as a discrete voxel grid, like what happens in the classical methods. And this is actually one of the great advantages of SVORT, because it basically just means that we have a resolution agnostic image during inference. So to reconstruct the 3D volume, SVORT takes this continuous forward model instead of the discrete formulation that we have in classical methods. So the difference here is that our volume, bias field, and noise are now modeled as continuous functions of the 3D spatial locations that we have, and NESVOR just treats these as learnable functions that are parameterized by these 3 MLPs that you can see here. So the overall pipeline just starts by first sampling these 3D coordinates that go through this hash grid encoding that I won't go into much detail, but is necessary. And basically the outputs from this encoding go into the 3 different MLPs that then are able to regress our bias field, our intensity in the volumes, and the variance of our noise. So overall, during training, our 3D model is reconstructed then by minimizing this error between our simulated and acquired pixel intensity values. So finally, I'm just showing here as well some of the NESVOR reconstruction results against the classical SVR method. And like I was saying, one of the advantages of NESVOR is that at inference we have this resolution agnostic model, really. So at inference we can output this volume in whatever resolution we want to. So this also kind of propagates then to the fact that NESVOR can be seen as taking less time to run, because we don't need to retrain this model for different voxel spacings. So we just train it once, and then we can use that trained model to get our final reconstructed volume at different entrances, which the classical methods don't do. So finally, just as more of conclusion and discussion, SVR is quite essential for constructing high quality 3D fetal images, and in particular when we have severe motion in subjects. So we've just showed some of applications that we can have in brain, body, and cardiac fetal scans. And all of these reconstruction processes are quite vital to then study early fetal development and detect abnormalities. So for classical approaches for SVR, these are usually just based on iterative motion estimation and super resolution reconstruction, and are still actively used nowadays. So they are quite reliable physics-informed methods, but they can sometimes be time-consuming and computationally extensive. Machine learning, however, has recently showed approaches to try and do SVR, and it's still quite a hot topic in research, especially by applying these implicit neural representations and transformers. So even though they can be quite data-driven and flexible frameworks with great potential to speed up these processes, they can still sometimes lack interpretability. So thank you, everyone.
Will you take questions? Does anyone have any questions?